Okay, welcome back. So now Dan is gonna get us going again with soft theorems and infinite dimensional geometry. Take it away.
Great, thanks. So first of all, just thank you again to the organizers for inviting me to speak here. I've had an amazing time. It's been a really fantastic workshop. I'm going to discuss some work in progress, which is sort of a follow-up to the paper that I wrote with Albert and Shruti. The title of the project is Soft Theorems and Infinite Dimensional Geometry. But basically what I'm going to discuss is just what is sort of an apparent ambiguity in the definition of the Yang-Mills S-matrix in the Coulomb phase and the relation of that fact to celestial conformal field theory and flat holography. So those S-matrix elements, they can just be computed in perturbation theory, and they are unambiguous for finite non-zero momenta, but the multi-soft limits in non-abelian gauge theory, where the wavelengths of more than one gluon are going to infinity at approximately the same rate, depend on the order of limits, and so they look ambiguous. That ambiguity can be quantified using the antisymmetric double soft theorems, which are universal statements. They are non-vanishing for any non-abelian gauge group, and this is a particularly simple expression which I've come across. But they basically say if you take, the limit of one momenta to zero, and then another, and then you do the opposite, it's not the same observable. Now, I think it's fair to say that there's been some confusion regarding the interpretation of this fact and its implications for flat holography, and I think I finally understand the resolution, and that's basically what I'm going to try to describe. So, and also, please feel free to interrupt me with lots of questions. Sure. Sorry? Yeah, so in this formula, I and J are basically color indices, A and B are polarization indices. So those are just the D transverse polarizations in D+2 dimensions. X and Y are the momenta of the two gluons which you take soft, which corresponds to points on the celestial sphere, which is just sectional cut of the null cone. And these I's here, they're just the conformally covariant tensor. It's just like dA dB of a logarithm. Great. So strictly speaking, the soft limit requires you to sort of consider the boundary of the domain of definition for the S matrix. So we could equivalently phrase this ambiguity as sort of an ambiguity in the extension of the S matrix to a particular boundary of kinematic space. And I think there's been a question, is there some right definition for these multi-soft limits? I've always felt that any prescription that you came up with was going to appear somewhat arbitrary, and that's sort of, well, maybe it's not a huge problem for the S matrix, viewed as a bulk S matrix, but it's important in celestial conformal field theory because soft gluons correspond to non-abelian conserved currents, and then there's a question of whether or not their correlation functions might be ambiguous. So my claim is going to be that there's actually an infinite dimensional geometric interpretation of this fact about S matrix elements, and the basic idea is just sort of a huge generalization of the idea in Albert's talk. So the idea is that the soft limits don't commute, basically because S matrix elements in Yang-Mills theory, they're actually sections of bundles over this huge infinite dimensional space of vacua, which I'll call curlium to distinguish from the finite dimensional example. And in the cases that we know, this curlium has local coordinates which are just trivial G connections at spatial infinity. Okay? So that's going to be the idea. And then if we just follow our nose, we'll find that insertions of soft gluons in the S matrix are just enacting parallel transport around this infinite dimensional space of vacua. And we will interpret the antisymmetric double soft limit just as computing this holonomy around an infinitesimal parallelogram in that space. That's also known as the Riemann curvature. So in other words, we just had this formula on the last slide, but you take two soft limits and disymmetrize, that's like taking functional derivatives on this space of trivial connections. So the polarization of the gluons just becomes the index on the connection, color indices match, and the real important point is just that there is now momentum, aka position dependence on the right-hand side, in contrast to the nonlinear sigma model. That's sort of what tells you that you're working with the space of functions, not a finite dimensional manifold, okay? Yeah, so I just said this, but these flat connections, they're just the local coordinates on this infinite dimensional space. And we're just going to reinterpret the fact that the antisymmetric double soft limit doesn't vanish as the fact that the vacuum manifold for Yang-Mills theory in flat space in the Coulomb phase is curved. This space M is basically going to be the space of maps from spatial infinity into G, mod G. It's always going to be basically the Goldstone space mod the global symmetry group, which is not broken on the vacuum. So it's going to be some infinite dimensional coset space. And those actually are well studied, not necessarily with the metrics that we're going to encounter, but there is a lot. Yeah, that's a very subtle question. I don't think I have a fantastic answer for that right now. Sort of trying to fill in the order zero piece of this story first. Any other questions? No? This is just an introduction. These are the cartoons. We will discuss exactly what this covariant derivative means later on. But at least, just think of this as an infinite dimensional version of the formula in Albert's talk, which was just nabla I, nabla J, but now I and J are basically infinite dimensional indices, okay? Okay, so in other words, there is no right definition for multi-soft limits in non-abelian gauge theory, just as there is no unique parallel transport between 2 points in a curved space. The result is path dependent, and the path dependent just means that inserting different orders of soft limits corresponds to different paths around the space of vacua, okay? So another thing which we can say is that in this language, the vanishing of antisymmetric double soft in gravity is a statement about flatness of the space of supertranslation vacua, and there's a similar statement for abelian gauge theory. Now, why is this interesting? Well, I think the existence of these vacua, we have all become relatively comfortable with the idea, but it is a very subtle boundary effect, which really only happens for gauge theories in the Coulomb phase on non-compact spaces. So, if you're an outsider to the field, you may be a little bit uncomfortable with the statement. But I think the point is that this geometric interpretation of double soft makes it clear that the moduli space of vacua is detectable just using standard perturbation theory techniques. So without any reference to asymptotic symmetries, charges, gauge transformations with non-compact support, you do a Feynman diagram calculation, interpret it appropriately, and that tells you about this infinite dimensional space of vacua. And in fact, these Feynman diagram calculations, they know more than just about the space, they can actually calculate its curvature, which I think is very interesting. So just to kind of put this in context of some older work, it's been known for some time that the antisymmetric double soft limit is kind of a discovery mechanism for hidden symmetries in the S matrix. So this old story about E77 and supergravity, what I'm describing is kind of an infinite dimensional version of that older story. But the fact that this case was known many years ago is kind of an indicator that these statements are all simpler and more familiar when the moduli space of vacua non-curly M is finite dimensional, okay? And that's basically the story that Albert just described. So in that case, the vacuum is determined by boundary conditions of local fields at spatial infinity, which give you coordinates on the vacuum manifold M, and the effective field theory about those vacua is just a sigma model with target space M. And it was shown in a very nice paper by Clip Chung and collaborators that single soft insertion of moduli scalar basically just gives you an operator which takes a derivative of correlation functions with respect to the vacuum manifold. Okay, so the physical interpretation of this formula was just that the zero mode of the moduli scalar, which is just the VEV, if you excite the zero mode, you're basically just infinitesimally shifting that boundary condition, right? Yeah. I don't think so. Well, no, I mean, we know exactly the soft theorem for at least, well, okay. Both in the sigma model and in Yang-Mills, you have to distinguish between a sort of the classical moduli space and the actual quantum mechanical moduli space whose metric can receive corrections. And I think that will happen in Yang-Mills. The leading soft theorem can get G Yang-Mills corrections, and that would correspond to corrections to the metric. But modulo that fact, we're really only using the leading soft theorem, which we know exactly. Okay, so if it receives corrections, we will interpret that as corrections to the metric, which is a familiar phenomena in the moduli space story. But modulo that, I don't think that there's anything. Yeah, just using the leading soft. That's the way. That's my current understanding. Okay, and what Albert just told you was that in celestial CFT, the existence of this soft moduli operator is equivalent to the existence of a marginal deformation in the conformal field theory. So the point to take away from that discussion was that the sigma model provides a finite dimensional family of celestial conformal field theories, basically labeled by boundary conditions, and changing that boundary condition meant turning on a background source for the marginal operator, or doing a marginal deformation. Now, multi-soft limits in the nonlinear sigma model did not commute, and the antisymmetric double soft theorem just measured the infinitesimal holonomy around the closed loop in that space. Okay, so these are all just formulas that you can check explicitly by hand in known examples. Now, in gauge theory, the identity that we have is the soft gluon theorem. A couple of things about this formula. So on the left-hand side, I'm inserting one of these residue operators that picks out the leading Weinberg pole. And you notice that I have a subscript in this notation, curly C is equal to 0. That subscript means that this S matrix element is calculated with a particular asymptotic boundary condition. In perturbation theory, that's always set equal to 0. But the point is really that finite energy boundary conditions in the Coulomb phase allow for a general flat connection there. And we'd like to interpret that formula as we did in the nonlinear sigma model. So the zero mode of the gluon, which we insert into the S matrix, infinitesimally shifts the boundary condition. So is the soft insertion really just a functional derivative on the space of trivial connections at spatial infinity? So is that a plausible statement? Is there any reason to think it should be true? Well, here's my heuristic, the way that I arrived at these results. We know that the soft operator is related in a somewhat simple way to currents in the celestial CFT dual. And there's a definition for a current correlator in terms of a background gauge field. So this formula says if you want to calculate correlation function of a current, you can calculate the correlation function in the presence of a background gauge field for that global symmetry, take a functional derivative with respect to the source, then set the source equal to 0, right? That formula looks a lot like this formula, right? Okay, and we're going to basically make this precise in the rest of the talk. And then we'll be led to interpret the antisymmetric double soft gluon theorem just as an infinite dimensional version of this formula that Albert showed you in his talk. Okay, so in other words, antisymmetric double soft in Yang-Mills computes an antisymmetrized double covariant derivative on these amplitudes. Now, there are a couple of important points between the nonlinear sigma model and gauge theory. The first is that the nonlinear sigma model soft limits don't have momentum dependence, and that is position dependence in celestial conformal field theory. One second, Noah. While the soft gluon limits do. And that's basically the big hint that the moduli space that we're dealing with here is infinite dimensional. It's a space of functions, not a finite dimensional manifold. Yeah, Noah? Mm-hmm. In this case, I think it's not that difficult because all of the different boundary conditions are related by symmetries. So there's a natural infinite G action on the space of vacuum, and I think probably they are related to each other by that action. But as far as I know, the only calculations, so it's very trivial in abelian models. It's just, some phase basically, because this connection basically just tells you how to parallel transport operators at scry. In the non-abelian case, it might be more complicated, but I think all the calculations that are actually done are done with the connection set to 0. Oh, it's just to make it look more like the nonlinear sigma model. I mean, we could probably rephrase all of these statements using a null Cauchy slice, but the point is just that I don't have to talk about null infinity at all in this talk, right? I have a soft operator. I can calculate its matrix elements just using perturbation theory. Forget about everything else. The formulas tell you that inserting that operator infinitesimally changes the boundary condition. And the only difference here is that the boundary condition is a function, not a number, right? Yeah. Oh, it was finite in the sigma model just because most of those moduli spaces are all finite dimensional. So, the space of Kähler and complex structures on a Calabi-Yau is just some finite dimensional space. Oh, it just gives you a finite dimensional conformal manifold. So, I mean, think about an ADS CFT, n equals 4 super Yang-Mills. That has an exactly marginal deformation, which is just the Yang-Mills coupling, and that corresponds to basically a boundary condition for the dilaton in the bulk of the ADS space, right? So there's some finite set of boundary conditions for massless fields in ADS, and that gives you a finite dimensional conformal manifold in the conformal field theory dual. Here, the kind of difference in flat space is that you actually have this infinite dimensional space of vacua, and that's why the soft behavior is a little bit more complicated. So sigma model is finite dimensional space of vacua, finite dimensional conformal manifold. My claim is that in gauge theory, there's, well, we have been saying for a long time, there's an infinite dimensional space of bulk vacua, and that corresponds basically to an infinite dimensional space of deformations that you can do in the celestial CFT. But there is an important difference that adding the 0 mode of a scalar does not violate Lorentz invariance. So the marginal deformation preserved conformal symmetry exactly. These boundary conditions for gauge fields and for gravitons, they are not, at least naively, Lorentz invariant. There's a whole industry of papers discussing the interaction of Lorentz invariance with large gauge transformations in flat space. Basic point is just that large gauge transformations don't commute with the Lorentz group, which is sort of related to this old problem of angular momentum in general relativity, which we now understand in terms of super translations. But the basic difference is just photons, gluons, gravitons have spin, scalars don't. So this set of deformations is a little bit different than the sigma model, but the kind of the lessons are the same. Mhm. It's not going to be space-time dependent, it's celestial sphere dependent. And yeah. So that's the point, right? This is an ordinary covariant derivative. This is a functional derivative. Yeah. Yeah. No, I don't think that the type of thing that I'm going to describe has ever been discussed in ordinary Euclidean conformal field theory. And that's kind of one of the points that I want to try to make, is that celestial conformal field theory is more than just a model with G symmetry, a model with global G symmetry, and this huge space of vacua. And that's going to be why there are aspects of celestial conformal field theory which naively look very different than ordinary Euclidean conformal field theories with G symmetry. That's going to be basically the conclusion, if I can get there. Yeah. Yeah, that's the statement. Well, yeah, it's basically just the fact that the boundary conditions in the sigma model don't have position dependence, and the boundary conditions can engage theory and gravity. You can have non-trivial flat 1 forms, but there aren't really any interesting non-trivial flat 0 forms. Okay. So I'm going to go very quickly through this because Albert just described it to you. But the main takeaway from his talk was just that when you have a continuous moduli space of vacuum in a bulk gravitational theory, that space can be parameterized by boundary conditions at spatial infinity, and those vevs give you local coordinates on the moduli space. I'm saying these because I'm going to make exactly the same statements again and again for gauge theory and for gravity. So I just kind of wanted to establish the chain of reasoning. Okay, so the effective field theory about these vevs is described by a sigma model with some metric and curvature on the moduli space of vacua. And the S matrix elements in that model, they carry this extra label, which tells you that they were computed with a particular boundary condition. And the observables that you compute will depend on which point in the moduli space you did the calculation. So when we calculate in perturbation theory, we expand the fields about their vevs and we integrate over the normalizable modes. And we get answers, physical observables, that are expressed in terms of the intrinsic geometry of this moduli space of vacuum. So for instance, soft limit of a moduli scalar was geometric. It just gave you the covariant derivative of the S matrix with respect to the vacuum parameters. And the interpretation was just that inserting this infinite wavelength mode is just like shifting the vev infinitesimally. So what you're really doing is just parallel transporting the model around the space of vacua. So you could define this leading soft moduli operator, its matrix elements were derivatives, and since it was a spin 0, dimension 0 operator, its shadow transform is a marginal operator. And I think that's a very important fact, because we can also think of the soft operator instead as a shadow transform of a marginal operator. And in that case, then the soft theorem is really just the formula for first order conformal perturbation theory in celestial conformal field theory. And if you'd like to do a finite deformation in celestial conformal field theory, then what you do is put in a coherent state of soft scalars. And that equivalently turns on a background source for the marginal operator in the dual. Now, when that moduli space was curved, the deformed observable became path dependent. So you took a little infinitesimal closed loop that computed the curvature at that point, and in celestial conformal field theory, that was interpreted as the curvature of the conformal manifold. Are there any questions before I go on to gauge theory and gravity? Okay. So in abelian gauge theory, finite energy boundary conditions allow for a trivial flat connection at spatial infinity. I'll call it curly C. Now, that boundary condition is invariant under global gauge transformations, but it spontaneously breaks all other U1 gauge transformations with non-compact support. So the space of allowed boundary conditions is just the orbit of this zero connection under the action of the gauge transformation. So the actual moduli space is just the space of trivial connections, which is curly G mod U1. Mod U1 because U1 kills the vacuum. It's preserved by the boundary condition. In the quantum theory, the S matrix elements, they carry an extra label corresponding to this boundary condition. Okay, and since that boundary condition spontaneously breaks this huge infinite dimensional symmetry, there's an associated Goldstone, which transforms as you would expect. In perturbation theory, all these calculations are done with the sort of simplest boundary condition. And with that boundary condition, you know what the soft photon theorem looks like. You can define a leading soft photon operator. And its matrix elements are very simple. They just factorize. You get this piece curly J, which is just a derivative of a logarithm weighted by charges. Okay, an important fact for us is going to be that a computation shows that the shadow transform of this soft operator obeys the ward identity for a conserved current. And now we'd like to try to reinterpret that soft photon theorem as a covariant derivative in the space of vacua, which in this case is the space of flat U1 connections, which is an infinite dimensional space. Okay, so can we have some formula like this, where we insert a soft photon that basically does a derivative with respect to the boundary condition that we computed the S matrix with? Now, the formula I think is plausible because classically the soft photon is symplectically paired with the Goldstone. And I think it's true that in higher dimensions it's symplectically paired with the shadow. I have to check that. But so upon quantization, you basically expect S to act like the momentum for this configuration space variable. So it does something like a derivative. Okay, so what we want to do is kind of make this precise. And we can do that in this case because the infrared sector of abelian gauge theory is exactly solvable. So we can actually derive and verify these statements. So last year, Prahar and I wrote a paper where we wrote down this soft action for the soft photon and the Goldstone mode, which basically computes everything that we know about the abelian the infrared sector of abelian gauge theory. So there's sort of a kinetic term for the soft photon, and then there's a shadow transform of the Goldstone mode, which couples linearly to the soft photon and a background source, which was the soft factor. Okay, and if you just compute in this model, if you want to know what is the correlation function of some M soft operators, okay, so you basically just integrate over the Goldstone mode. That's like a Lagrange multiplier that says S equal to curly J. So everything in the integrand just becomes soft factors, and this kinetic term just becomes the exponentiated soft exchange in gauge theory. Okay, so this action just is equivalent to the infrared sector of abelian gauge theory, computed with the boundary condition curly C is equal to 0. You can tell what's going to happen if we change this boundary condition, because this Goldstone, which is coupling linearly to S, is just going to pick up an extra piece corresponding to the non-zero boundary condition. And what that looks like is just that the boundary condition acts as a source, as a background source for the soft operator. Okay, But now you can just see, taking a derivative with respect to this background source is just going to bring down a factor of the soft operator. So that means that we can really view the soft theorem as a covariant derivative in the space of vacua. Equivalently, you can just do that path integral exactly, as I said, integrating over the Goldstone as a Lagrange multiplier, take a functional derivative, and you'll see that it just reproduces the soft photon matrix elements, okay? So we see that the soft photon insertion is just enacting parallel transport around the infinite dimensional vacuum manifold. If we move the shadow transform around in those formulas, there's an equivalent formula which says that the actual change in the boundary condition is just a background gauge field for the current. And I think that's kind of the cleanest and best way to think about this, because I think that the soft insertion is really a derived notion from this abelian current. So, the boundary condition is a source for the current, equivalently because the soft operator is shadow transform of the current. The shadow of the boundary condition is a source for the soft operator, okay? In the sigma model, changing the boundary condition for the bulk scalar turned on a source for the marginal operator dual to the soft scalar. So what is the deformation that we are doing corresponding to this change in the boundary condition in abelian gauge theory? Well, it's just turning on this current gauge field connection like you would have in electromagnetism. So you're turning on a background gauge field for the global U1 symmetry of the model. And, just as in the sigma model, if we turn on a coherent state of soft photons, that's just moving us a finite distance around the vacuum manifold. So you throw in an exponent of soft photons, and that just shifts the boundary condition by some amount, okay? And then we could ask whether or not that parallel transport is path dependent. In other words, is this space curved? We compute that with the antisymmetric double soft theorem, and it vanishes. So we say that the space is flat. And that's basically just because the infrared sector in abelian gauge theory is described by a linear model. So no interactions. That means that this infinite dimensional space is flat. Okay, so I'm going to just, there's a completely isomorphic set of statements for the super translation vacua in gravity. I'm just going to go very quickly through it. Again, finite energy boundary conditions basically allow you to pick a flat super translation connection as a boundary condition. It's invariant under global translations, but it breaks all of the other diffeomorphisms with non-compact support. So the moduli space is basically just super translations modulo global translations, okay? In the quantum theory, there's an extra label on S matrix elements corresponding to that boundary condition. You know what the soft graviton theorem looks like, and we'd like to interpret it as a functional derivative with respect to the space of super translation vacua. Again, we have an exact model for the infrared dynamics in gravity at leading order, because it is also effectively abelian. And, in the presence of an... okay, all right, then I'll go a little bit slower, sorry. Yeah, so, okay. You know what the soft theorem looks like. It's just a derivative operator on p log p. And we want to try to interpret this in analogy with the nonlinear sigma model in abelian gauge theory as an infinite dimensional functional derivative. So we expect a formula that looks like this. So I insert a soft graviton that takes a functional derivative with respect to the boundary condition that we computed the S matrix with. And we can check that explicitly, again, because the soft sector of gravity, even though gravity is a totally nonlinear theory, because the charge is energy, the soft sector has no charge. So it's also effectively abelian, which is what allows us to write down an exact action, which again reproduces everything that we know about the soft sector. So you insert some number of soft gravitons, and you get out factorized soft factors times the exponentiated soft exchange. Okay, again, just by doing the integral over the Goldstone, that sets the soft operator to the soft factor and turns the kinetic term into the infrared exchange term. Okay, and again, when there's a non-trivial boundary condition, because the Goldstone is just coupling linearly to the soft graviton operator, with a non-trivial boundary condition, you're just going to pick up basically a background term for the soft graviton operator, which means that when you take a functional derivative with respect to that background term, you will just pull down a factor of the soft graviton. Okay, equivalently, you can just do the path integral exactly, take the functional derivative, and you'll see that it gives you exactly the matrix element for the soft graviton. Okay, so the soft gravitons are parallel transporting you about the infinite dimensional vacuum manifold of supertranslations. And if we turn on a coherent state of soft gravitons, that's going to just do a deformation on the boundary condition that we computed the S matrix with. Okay, and then again, we can ask whether or not this parallel transport is path dependent. We answer that question with the antisymmetric double soft limit, and it turns out that it vanishes. Okay, so that space is also flat. And again, it's flat basically because it's described by a linear model. There are no interesting nonlinear effects in this action. Okay. Okay, are there any questions before I do non-abelian gauge theory? Okay. Okay, so I'm going to run the same set of words in gauge theory. So in the Coulomb phase, which means that we are not in the confining phase, finite energy boundary conditions in Yang-Mills theory allow a flat connection as a boundary condition for the gauge field. That boundary condition is invariant under the global G action, but it spontaneously breaks all other gauge transformations with non-compact support. And the allowed space of boundary conditions are just the orbit of this zero connection under the action of the gauge transformations on the d-dimensional sphere, which is spatial infinity. Okay, so the moduli space is going to be this curly G modulo global G, but now this already looks like it's some curved space, right? Like this is, as soon as you have a non-abelian Lie group, you know that there's going to be interesting geometry in the game. And in the quantum theory, the S matrix elements are going to carry a label corresponding to this boundary condition. Usually all the calculations that we do are with it set equals to 0, but the point is that there are infinitesimal deformations of those calculations, and those are going to be related to soft insertions of gluons. Okay, so you know what the soft gluon theorem looks like. We want to try to interpret it as a functional derivative on the space of vacua. Now here, the soft action has not been worked out for non-abelian gauge theory. That's actually one of the reasons that I'm doing this project, because I feel that this is one of the most important problems in our field to get correct. But we don't have that yet. But you can tell from all of the other arguments that this is always basically just a symmetry consideration. So you turn on a non-trivial boundary condition for the S matrix, and it always just turns on a background gauge field for the non-abelian current in the CFT dual, right? And then you know there's going to be a formula which says take functional derivative with respect to that background gauge field, set the background gauge field to 0. That's just the correlation function of the current. And we know that this formula is equivalent to the soft theorem via the shadow transform. Okay. So all of that is basically the same as in abelian gauge theory and gravity. The big difference is that abelian gauge theory and gravity, the soft limits commute, but they don't in Yang-Mills. Okay. So this formula says that if I take gluon with color index I, polarization A to 0 first, then the gluon with color index J, polarization B, which I interpret as doing two covariant derivatives with respect to these boundary conditions. And then I do the opposite order. I get something which is non-zero, which I managed to get in this sort of very interesting factorized form. So normally this antisymmetric double soft is written in terms of these sort of less transparent kinematic variables, but if you work hard, you can find a much simpler expression, and it has a couple of characteristic features of infinite dimensional curvature. So for one thing, even though you took two soft limits, the answer actually only has a single sum over the remaining hard external particles. And that should be the case if it's acting as curvature. There would be a double sum in the simultaneous soft limit, whose geometric interpretation I think is unclear, and I'll say a little bit more about it later on. And you can also see that this curvature is going to be singular when x goes to y. And that's a familiar statement in infinite dimensional geometry because infinite dimensional trace and the Ricci tensor are usually ill-defined in these geometries. So normally, what can go wrong when you move from finite dimensional geometry to infinite dimensional geometry? Well, basically things can fail to converge. So it's okay basically to talk about curvatures, but if you try to take traces, you get infinity and you have to regulate it in one way or another, point splitting, something like that. But as far as the curvature is concerned, it's totally well defined, and this is basically what it is. I view this basically as Feynman diagrams computing the curvature of the space that we're interested in. Okay? All right, so now I'm just gonna, so those are sort of the main results, and I just want to tell you what I'm thinking about next. So I think it would be a huge advance to finally produce a 2D action that computes soft exchange and soft emission in non-abelian gauge theory, order by order imperturbation theory. But it's always confused me how to make a 2D model that accounts for the non-commutativity of soft limits. So you really want a d-dimensional celestial system which reproduces everything that you know about the bulk S matrix. And for a long time, it was very difficult for me to even understand how to phrase this non-commutativity in intrinsically two-dimensional language rather than four-dimensional language. Basically because once you get to the two-dimensional language, you've already forgotten about all of the energies. What would it mean to insert one thing before another? There's really no notion of insert this local operator first and this local operator in a single Euclidean conformal field theory. But I hope I've convinced you that non-commuting soft gluon limits is really a crucial part of the bulk gauge theory, and it's a reflection of properties that we believe are crucial in celestial conformal field theory. It's really a feature, not a bug, so it should have a natural expression in celestial conformal field theory, not some Baroque expression that involves, picking some particular prescription for soft limits, and then, or are the current correlation functions ambiguous, who knows? I think the key is just that celestial conformal field theory is more than a d-dimensional system with G-symmetry. It has G-symmetry, unbroken G-symmetry, but it also has this huge space of vacua, which basically correspond to different soft profiles. And that space has an interesting geometry, which is curved. And so in answer to a previous question, this is highly unusual for an ordinary garden variety Euclidean conformal field theory. This is something which is sort of very different, but I think we have to confront it. Celestial CFT is just going to be different than ADS CFT. Okay, so I think I finally understand the resolution to that puzzle, and I mentioned it during the question session in Albert's talk, but you could kind of ask the same question about the sigma model and its celestial CFT dual. So there we had a statement that the antisymmetric soft limits in the sigma model computed the curvature of the conformal manifold. But the conformal manifold is definable purely within conformal field theory. There's nothing funny about that. So how is it? How is it that we get sort of this order of limits from something which looks like it's defined purely within conformal field theory? Well, marginal operators are local operators. It doesn't make any sense to say I insert this one first or that one first. But their shadows are really the soft scalars. And so if we view those shadows as integrated deformations, then it does matter in which order you do deformations. Okay, so a single conformal field theory, it doesn't really make any sense to say first I inserted this then I inserted this. But if you're doing deformations of conformal field theories, then it is actually very important that you say which order you did the deformations, because generically there will be curvature and there will be Holography. Okay? So for instance, in ordinary Euclidean conformal field theory, the curvature can be calculated by anti-symmetrizing some integrated 4-point function of marginal operators. Albert showed you the exact formula, but basically the metric is 2-point function of marginal operators, and inserting shadows of marginal operators is like taking derivatives. So 2 derivatives on the metric is like a twice integrated 4-point function. And the local operators in this correlator behave like normal operators. You don't say you inserted this one first or that one first. But this quantity is generically divergent because you're integrating over things with coincident point singularities. And so it has to be regulated, and that breaks all of the standard axioms of standard single Euclidean conformal field theory. And that's kind of how we get non-commutativity out of a Euclidean conformal field theory. Okay? So, my guess is that we should view the soft gluon in the same way, as sort of an integrated operator, a deformation of the celestial conformal field theory. And then it does not need to commute in the same way that a normal local operator does, if we view the current as fundamental and the soft insertion as its shadow, as doing a deformation in the space of vacua, because then you have to say which deformation did you do first. Okay? So that's what I think. Here's just 3 lines of speculation. So lots of people ask about simultaneous soft limits and other limits which I would view as bad because they don't really have nice geometric interpretations. And I think there might be some way to phrase that as sort of scheme-dependent quantities when doing conformal perturbation theory in celestial CFT. I think that this interpretation does make it plausible that there really is a unique celestial conformal field theory capable of reproducing all the infrared behavior of Yang-Mills scattering amplitudes that does incorporate non-commuting soft limits in a very natural way, basically this line here. So I think it's very important to try to find this action and start computing with it. And just one final piece of speculation, in the sigma model, all of the physical observables were actually expressible in terms of the geometry of the finite dimensional vacuum manifold M. I think it would be interesting to know whether or not the observables in Yang-Mills theory are expressible in terms of the intrinsic geometry of this infinite dimensional manifold curly M. So we already know some quantities that are easily expressed in terms of that infinite dimensional geometry, but maybe that's a more general phenomena in Yang-Mills theory and an interesting organizational tool for calculations. So that's all I wanted to say.
Maybe about the last one, like who likes to explain the that makes that but it might get the effect of
yeah, well, I think this is totally non-obvious. I mean, given the fact that I'm like, 8 years into this program and only now it even occurs to me as a possibility. So I think it would certainly be non-trivial, but, given the analogy with the nonlinear sigma model, it might be possible, but I really, this is pure speculation. I don't really even know how to start. No? Yeah, you would do regular background field method, but it's a physical background field. You're actually expanding around a non-trivial connection. I'm not sure if I completely understand your question. I think, so the only place where I think it is the least bit confusing is in 4 dimensions, because in 4 dimensions, single insertions of shadows actually localize back to the operator itself. There might be something funny with multiple insertions of shadow operators, precisely because then you are dealing with, in my language, multiple integrated correlation functions, which can be scheme dependent and which require some definition. In higher dimensions, there's just no question. The soft operator is not the current. It doesn't even have the right dimensions, so the question doesn't even make sense. In 4 dimensions, I admit it confuses me a little bit, but 4 dimensions confuses me for lots of reasons, because 4D gauge theory is more like 2-dimensional nonlinear sigma model, and 2 dimensions is very special for nonlinear sigma model. That's the one where it's asymptotically free, has strong coupling behavior, and actually tends to restore the symmetry and kick you out of the broken phase. So there are lots of confusing things about 4 dimensions, which are not really confusing in higher dimensions, but I agree, I have to think a little bit about the 4-dimensional case. But I would say that there might be something subtle when you try to insert multiple soft operators and claim that those are the same as multiple current insertions, because then really that formula is hiding multiple integrals, which can have divergences, and you have to be careful with those. Well, I don't want to make a super general statement. The only one that I have any degree of confidence with is sort of this special set of the soft operators and their shadows. I don't know about the general principal series operator. I think, to me, it's relatively clear for these integer dimension operators that the fundamental thing is really the operator that we would have thought was fundamental anyway, and that these are sort of derived operators that act as deformations. But I don't want to make any general claim about the operator spectrum of the full model. I'm not sure. Well, I mean, there's this funny thing that on the principal series, there's really no difference between shadowed representations, right? That it's supposed to be actually the same. So something funny might be happening there, but I don't think I have a good answer to your question. Maybe we can discuss afterwards.
They also talk about geometric theorems
Yeah, I don't know. I looked at that paper briefly and I didn't quite manage to understand it. I think it is intrinsically different than this picture, but this picture feels very natural to me given the nonlinear sigma model. I don't completely understand the relation to their work, but it would be interesting to understand it. Yeah. Yeah. Deformation. Yeah, I mean, that's always kind of been, people haven't really said it in this language, but the picture has always been that the super translations are broken on the vacuum, the translations are preserved. Yeah, but that means that at that given point, the super translations are not by themselves actual symmetry, right? Because when you act with them on the vacuum, you create a soft particle. That means that they're spontaneously broken. So you only have the exact global part of the symmetry at a point, and everything else is deformations into the space of vacua around that point.
Are there any more questions, Noah?
Could you speak up just a little bit? Yeah, I mean, why am I interested in this curvature at all? Well, one reason is that I really want to know what this 2D action is that computes soft exchange and non-abelian gauge theory. I'm interested in this analogy because 4D gauge theory behaves much like the two-dimensional nonlinear sigma model. So both are asymptotically free, both generate non-perturbative mass gaps, they gap each other out and in some sense put themselves back into the disordered phase, right? So I really want to know what this action is, but it's much more difficult than the abelian cases. But you see, what is an infinite dimensional metric? Well, it's basically a kinetic term, right? Maybe with some corrections. And so, the fact that these other ones had flat metrics just corresponded to the fact that the infrared model was just a free theory, very simple correlation functions, no corrections in the coupling. What I'd really like to know is what is the metric on this field space for the two-dimensional model, because I think that that model will compute infrared exchange in non-abelian gauge theory. And then you know a lot more about the physics of two-dimensional models than four-dimensional models. And really what do you really want to do in non-abelian gauge theory? We know how to compute very high energy processes because model is essentially free, it's asymptotically free. You really want to solve just for the very low energy part of the spectrum. And that's exactly what this model would compute for you. So, I view this basically as a piece of data for the kind of leading order metric that we're going to encounter when we find this model that computes soft exchange. So that's kind of where I'm headed with this expression.
Okay, well, let's thank Dan again for a very interesting talk. And we'll get Gotham set up here.